The iPlug project is focused on developing multiport converters for low and medium voltage applications, capable of integrating various power appliances, generation systems, distribution lines, and loads. These converters utilize control techniques for more than 2 ports, making their control more complex than traditional converters with single input-output sections. Multiport converters are categorized into 3 main groups: isolated, non-isolated, and partially isolated multiport converters. Isolated multiport converters use power transformers for galvanic isolation, while non-isolated converters maintain direct physical connections between ports. Partially isolated multiport converters combine isolated and non-isolated sections, offering a flexible and advanced solution for efficient power conversion.
Well, before iPlug, there was no formal assessment of multi-port converter topologies and try to identify what is the best suited topology depending on the application, and this is one of the highlights that we have provided in iPlug. We have provided a matrix approach where the user can introduce their needs and what they have, and later on they can find what's the best suited converter topology for this application.
So for our medium voltage multi-port converters, we use the results of work package 1 to identify different families of topologies that we thought would be really effective for these applications. We refined the topologies down to what we thought were the most feasible and suitable topologies, and we then compared the winners of those 2 different families of topologies in more detail. So we used component count as a proxy for cost and size, and we compared other features like operational complexity, robustness, flexibility, modularity, and wider operational characteristics.
At medium voltage, multiport converters are primarily used in distribution grids to connect systems operating at the same or different voltage levels. These converters enhance voltage management and optimize power distribution, while also enabling the integration of distributed generation sources, energy storage systems, or electric vehicle charging stations. The main contributions of iPlug project in relation to medium voltage multiport converters are defining and evaluating several candidate multiport converter topologies with multilevel converter configurations as building blocks. Implement control strategies for isolated and non-isolated multiport converters. Develop and validate isolated and partially isolated multiport converter topologies with laboratory prototypes and control hardware in the loop setups.
First of all, we have criteria to meet and an application we want to develop this multi-port. And then we have multiple solutions. So what we did then, that we check if they perform the way we want them in terms of dynamic performance in normal conditions, some abnormal faulty conditions. And in terms of cost, flexibility, modularity, we have indices to compare them and finally come with a figure that a certain topology is better. So that has been done in one of the tasks, and then we will test more the final topology we have.
So what we offer is the environment for model-based engineering that enables the users to run the whole chain from offline simulation to the real hardware testing. So our part there is to provide the solution and the support for our customers for them to execute successfully.
We first of all started with some simplified models, and we started doing some offline simulations to test them. And once we checked that the control strategies that we were proposing were behaving as we expected, we also started doing some hardware in the loop validations with Typhoon Hill devices. And also the idea is to do some laboratory tests.
We have 2 ways. In general, as in academia, we use simulations first. So we test some simulations, and the topology we come up with is the best solution for the application in question. So what we do is that we try to develop a low power scale version of the topology we come up with, and then we verify that it works as we intended, as it is intended in both normal conditions and abnormal.
So my part in the iPlug project was supporting the researchers in order for them to successfully use our solution. Mainly the part with the transitioning to the C-Hill setup. So in order to do that, we need to deploy the control code to the external controller. In that way, the users run their external controller that is interfaced with the device.
So some of the challenges with deploying novel converter designs like multi-port converters for real grid applications is that these converters are new, they need to be tested, they need to be validated before they're put into the grid. If you just take a converter design and you model it perfectly, you get all the topologies resolved the way you want it to, and then try to deploy such an equipment directly into the grid, it could be that your control is not paying attention to constraints that can occur with the real system. So it may have specific behaviors that the hardware itself doesn't allow it to run that you don't run into when you're running a model on your computer. And this can lead to really destructive outcomes. You may have resonance effects where the converter actually starts resulting in behaviors that can destroy the equipment that is connected to it. So what is important is that when we're developing these control designs, we take the chance to be able to test these controls directly on the real control hardware in a way that the control hardware doesn't know the difference between the modeled converter and the real system. And for that, we use controller hardware in the loop.
We have a lot of experience from modular multi-level converters for high voltage applications, and we decided to use it also for multi-port converters, because here we see that modular multi-level topologies have more flexible control, and that can be used to ensure a robust operation of multiple converters.
At low voltage, multiport converters can be utilized both in distribution grids and within buildings. Integrating multiport converters into residential installations offers significant benefits, including improved system efficiency and reduced costs for integrating renewable energy sources, electric vehicles, and energy storage, compared to conventional methods. The main contributions of the iPlug project in relation to low-voltage multiport converters are development of novel non-isolated topologies for residential applications, performance evaluation of multiport converter topologies based on renewable source mission profile, implementing control strategies for isolated and non-isolated multiport converters, validation of isolated multiport converters with laboratory prototypes.
Regarding how we evaluated the different topology, work package 3, we approach different solutions, including isolation and non-isolated converters. The key point was to find the best solution in terms of efficiency and power density, because different solutions, depending on the device that you're using, can be evaluated in a different perspective. So we did several analyses, try to find with a single switch, try to use multiple functions. So the idea of a specific work package is to use a single switch not to operate for the single converter, but to operate in a multiple port, so doing more functionality. Of course, in principle, we will save cost on the overall equipment, and the major goal of the research was also to show the level of efficiency we are able to achieve, the level of power density, as well as the level of controllability that we are able to achieve in these new and innovative converter topologies.
We have a comprehensive approach for validating the control. We start first with the modeling and verification using the simulation softwares. We have developed both linear and non-linear control of the multiport converter. And after we validated this using simulation, we moved into hardware implementation. And we have validated the performance experimentally under various operating conditions. We have step changes at the power level to different ports, and also we have a change on the AC and DC sides, and the performance of the controller showed a good dynamic behavior comparable to conventional two-port converters.
We have validated our converter topologies and control with different methods. The first one was to use, of course, first some simulation tools
which enable us to verify all the analytical and theoretical analysis that we perform, and a numerical simulation are able also to validate both control and also power stage design. The second step, which also with a partner that we have of course in the iPlug project, was to use hardware in the loop, which means that all the converter is simulated in real time, while the control part is directly implemented in the control card. This enables to the full validation of the control part in a physical environment, while all the power converter is actually simulated. The last step that we did here at our power electronics laboratory in Padova, and more specifically in an off-site campus in Vicenza, was also to build the physical converter and to physically also realize the kind of performance in terms of efficiency and controllability that we were able to achieve.
The partners in the project have used initially Titan's offline simulator software to match the model performance that they previously developed in that lab with the real system. And from that, they then transferred that model from Titan's into the real-time testing applications.
We have contributed in work package 3 to design non-linear control for no-isolate multi-port control. Designed for microgrid with our partners.
I think we developed a new solution, especially extending an existing topology in a new approach, being able to build up the multi-port configuration, both in three-phase and single-phase one. I think this to be a kind of a new solution, as well as some control part. Together with some PhD students, we developed a new passivity approach, so all these converters can be easily deployed on the network and also enable damping behavior of existing oscillation in network, enable more penetration of power electronic system and therefore multi-port converter in distribution grids.
Multiport converter topologies for medium and low voltage applications have been extensively analyzed, with the most promising solutions implemented and validated through laboratory setups. These topologies are expected to be adopted by power electronics manufacturers in the near future. iPlug. Innovative power electronics solutions for a greener electrical grid.